So we talked on Monday about organizing data, putting in these tables, making these graphs. Today we're going to look at summarizing it numerically. The way it looks, by the way, for those of you that don't know, I won't be here tomorrow, so this class will not meet tomorrow. I'm going to be in Richmond all day. Our Unit 4 test was scheduled for Monday. I'm actually going to move that back. I want to chirp about statistics a little bit more on Monday. So Wednesday we will take our Unit 4 test. And if people need more time, we'll have the class on Thursday to finish it up. But the intention is to have them graded so I can give them back to you on Thursday, and you can do corrections if needed on Thursday in class. So that you can walk out of here Thursday done. And the last day of class is next Friday. So the last day of this class will be next Thursday. We're just not going to do the final. We'll just do that last unit test, and we'll call that good. The final is to evaluate the course, not the students, anyway. So I can get away with one semester skipping it. But I will post a recording for tomorrow that's actually a review recording going over all the stuff because there's a lot of stuff in this fourth unit here that we're doing. So that'll give you something to view while you're sitting around missing me in class. The fourth unit, I don't want to take time and list through it right now, but it's just the areas, volumes, measurement conversions, and then the statistics that we're doing. So yes, remember, tomorrow I won't be here, so don't come into class looking for me. But that recording will be out there for you to summarize everything. So, summarizing data numerically. We have to talk a little bit about distributions of data. And we looked a little bit yesterday at, organizing tables. Monday at organizing tables and creating graphs. And that's a form of a distribution. But to understand distributions, we need to get down to their rawest form. So let's say that we have numbers here. I'm looking at maybe grades on a test. And let's say the grades range from 80 up to 95. 95 is the highest grade, 80 is the lowest grade. A pretty tight group. And so what we would do is we would display the scores. So let's say I grade the first test and it has a score of 84. So we put a dot at 84. Score the next test, it has a score of 91. So I'll put a dot at 91. Grade the next test, it's an 87. The next one's an 86. Then I might have another 87. So I'm going to put a dot above it since there's already one there. Next one might be a 90. Then an 81. And 85. 93. 88. And as I'm grading the test, every time I grade one, another 88. Another 86 and 87. So as I grade the tests, I put these dots on this number line to map them out. And as I put more and more on there, it creates a distinguishable shape. That shape is called a distribution. Now, just from the dots that I put up here, it's starting to form that shape, but most distributions form a bell shape. You've probably heard of the bell curve before, or grading on a curve. This is what it's referring to, is looking at that distribution in that bell curve. The technical name for that is called a normal distribution. In statistics and in nature, data tends to be distributed in that bell curve. So it's called a normal distribution because that's the shape that data normally is distributed in. Heights of people would form a bell curve. Usually grades on a good test would form a bell curve if there's enough people being tested. Your wages, if you looked at average wage of people, would form a bell curve. So to describe this distribution or this curve, again, we're looking at it over a number line. I'm going to redraw the number line without dots above it. So the curve might look something like this. Then there's my bell curve. Well, to describe this curve, one thing I might do is say, hey, the center is approximately at 87. That's describing the center of that curve. So if I were going to compare this curve to, let's say, this green one, let's say sits there. Well, that green one, I would say, has a center at about 90. Now, I traced the blue curve to make the green one so they're the same shape. It's just the center has moved. So we've moved the center, changed the center. Now back to that blue curve, I might have another one that looks something like this. The center of that purple curve is also at 87. So it has the same center as the blue curve. How would you describe the difference between the blue and the purple? Yeah, steeper and skinnier, yep, or narrower. The term is spread. The blue curve is more spread out. The purple curve is narrower or less spread out. A technical term for that is dispersion. How dispersed are the points? So we're going to describe those distributions by describing their center and their spread. So describe center, and I'm actually going to cheat a little bit here for a minute. Oh, yeah, that's not what I want. I want this one. There we go. I'm just doing this so I can make a list of numbers and have them always there. My computer's acting up lately. So there. Okay, so what I'm going to do is I'm going to create a list of numbers over here. So my list of numbers are going to be, oh, let's just do 8, 19, 27, 15, 17, 11, 32, and 17. So there's a list of 8 numbers. That's my list of numbers. If I want to describe the center of those numbers, there are actually several different things I can use. One of the more common ones is something called the mean. The mean is what most of us would refer to as the average. It is found, just like we've been doing this probably since about 3rd grade, calculating the average of a set of numbers. You add them up. The symbol for that is this symbol here. It's called sigma. That means sum of. Add up the numbers, add up all the x's, and you divide by n. N is the number in the list, in the set is the term we use. So how many are in here? 8. So for this set, n equals 8. So we would add them all up. 8 plus 19 plus 27 plus 15 plus 17 plus 11 plus 32 plus 17 divided by 8. Well, what's that add up to? We got 17, 44, 59, 76, 87, 119, 136 over 8, it looks like. So that 17 is our mean. Does that look correct? Nobody's playing along at home?
I have a question on that though.
Yeah.
Like, I know how to do that, but will the mean always be a number that's in the list?
No. I actually expected this to come out to be a decimal, like 16.625 or something like that. And the mean will often turn out to be a decimal like that. The biggest thing is when you're doing this, when you're punching it in the calculator, when you get to this point where you've punched them all in, adding them up, hit equals first, then divide by 8. Because if you just hit divided by 8, it'll divide the last number by 8 and add it to the rest of them. So make sure you hit equals. And I did screw something up. So it was 146 at 136. So it did come out, it should have been 18.25. See, you guys shouldn't have trusted me. So 18.25 is my mean. I dropped a 10 somewhere when I was adding. Oh well. So anyway, 18.25 comes out to be my mean. The next one we want to discuss is something called the median. The median is the middle number. So that one has two things you have to do. The first thing you have to do for the median is you have to put them in order. So I'm going to go over here and I'm going to put these in order from smallest to largest. What's my smallest one? 8. Next one? 11, and then 15, and then 17's in there twice, and then 19, 27, and 32. I have 1, 2, 3, 4, 5, 6, 7, 8, and I had 8 to begin with. So I just wanted to make sure I had them all in there. So there we have them all. So I put them in order from smallest to largest. That is the first thing I need to do. So back over here, second thing I need to do is find the position. To find the position of that median, you take n times 1/2, or 0.5, because it's the middle, halfway. Well, n is 8, right? So what's 8 times 1/2? You get 4. There's two possibilities here. What I got here is a whole number, right? When you get a whole number, that's telling us it is between that one and the next. So it's between, that one is the 4th number, the next number would be the 5th number. 4th and 5th numbers in my list over here are 17 and 17. Well, what's between 17 and 17? 17, right? Or nothing, they're together. And when you're doing it between two numbers, technically what you should do is average those two together. 17 plus 17 over 2 is 17. So 17 is my median. What if it did not come out to a whole number? Let's say, for example, and so I'm not using these numbers over here anymore. Let's say, for example, that n equals 11. So I would do 11 times 1/2, which is 5.5. If that's a decimal, instead of a whole number it was between that one and the next one. If it's a decimal, you round up. So the 6th number in the list is the median.
So pretty much you just look at if it's an odd number of numbers.
Yes.
You round it up if it's an even number.
If it's an even number, if n is even, it's going to be between two of the numbers. If n is odd, you're going to round up and it's going to be one of the numbers. So here it would be the 6th number in the list, because that puts 5 before it and 5 after it, so it's still in the middle. The next measure of center is something called the mode. The mode is the number that occurs most often. Now, most smaller data sets like this don't have a mode. This one actually does. What number appears most often? 17. There are other measures of center. There's things called the mid-range. The mid-range is found by just averaging together the smallest number and the largest number. It's called min plus max. Smallest number and largest number divided by 2 would give you the mid-range. So here that would be 8 plus 32 divided by 2. Well, 8 plus 32 is 40. 40 divided by 2 is 20. You can see that's not very close to the other ones, is it? In a perfect set of data, in a normally distributed set of data, the mean, the median, and the mode would all be the same number. The closer they are to being the same, the closer this is to being a normally distributed set of data. Now, with a small set like this, n only equals 8, we don't expect it to be perfectly normal. If we had like 150 numbers, we'd expect it to be really, really close to being those 3 numbers being the same if it's a normally distributed data. Now, we could talk about being skewed. What skewed means is that it's not lined up. It's not a symmetrical bell curve. Now, that bell curve is symmetrical. You cut it down the middle and fold one side onto the other, and it would fold right over on top of itself. If it's skewed, well, then it's not symmetrical anymore. Like this here is what we would call skewed left. It's been stretched out to the left. So in that data set, the mode is still right at the peak. The median usually moves a little bit. And depending on how skewed it is out here, the mean is the one that probably moves the most. If I were to ask you what is the best measure of center, mean, median, or mode, what would you say? A lot of people say mean because it's the one they've been doing since like 3rd grade, averaging, adding them up and dividing. Right? It feels like you're doing more. But let's take this set of numbers over here for a second. And I'm going to add a 9th number to this set. The 9th number that I'm going to add to this set is going to be, what is that? It was 146 that added up to. Let's add 64. Let's put 64 in there. Now when I add those numbers up, it adds to 210. Let's get back here. Where'd it go? Here we are. So now when I add these up, that's the 210, and now n is not 8 anymore, it's 9, right? So that's going to divide out to be 23.33, right? 23 1/3. Well, that changed significantly just by putting one different number in there. It went from 18.25 all the way up to 23. That's mean. How has the median changed? Well, the median, they're in order. 9 times 1/2 is 4.5, right? So that means we're going to round up. The fifth number is the median. Well, the fifth number is 17. The median here hasn't changed. The median is considered to be more stable. The best example of this I can give, I don't remember now if it was 1983 or 1984. I believe it was 1983. University of Virginia advertised that the average starting salary of a 4-year marketing graduate was right around $78,000 per year. That's a pretty impressive number. That's a pretty impressive number by today's standards to get a bachelor's degree and start out at $78,000 a year. Back in 1983, it was even more impressive. In 1983, your average high school teacher was starting out around $16,000 or $17,000 a year. So $78,000 was a pretty good salary. What they did not disclose was that one of those marketing graduates who did graduate with a degree in marketing was a young man by the name of Ralph Sampson. Ralph Sampson was 7'4", was the two-time NCAA basketball player of the year, was drafted number 1 by the Houston Rockets. You think he made $78,000 that year? No, he had a multi-million-dollar contract. It takes a lot of $20,000 marketing graduates to average a multi-million-dollar contract down to $78,000. Mr. Sampson was the only one in that group that made more than $33,000 that year. This was a mean, obviously. His one extremely high salary changed it that much. The median for that group was right around 26. What's that? Well, it wasn't average, but they didn't specify what type of average. A mean, you just add them all up and divide by how many there are. Well, you got that one really extreme number, like this multi-million-dollar contract. It changes that mean a lot. Like over here, when we added the 64, the mean went up to 23 from 18, but the median stayed 17. So the median doesn't change as much if you put one really high or one really low value in there. The mean changes a lot and the median doesn't.
Do they do that a lot when they advertise, like if you want to go into a career field, they're like, oh, the average amount you make.
You got 1 million you're throwing in there? Yes and no. I mean, if you're really being honest with, there's a whole thing of statistics, and it's one of the things that I harp on when I teach a statistics class, is statistical ethics. Really, there are things called outliers, and outliers are numbers that don't fit in with the rest of them. Like the 64 here is twice as big as any of the other numbers in the list. You have to decide whether that's a valid number to include in that list or not. That 64, depending on what this list of numbers describes, might be a very valid data point and we might have to keep it in there. Or it might be something unusual happened. Like in the salary case, well, an NBA basketball player, it didn't matter what degree he had, any degree. He could have dropped out of college after his junior year and still made millions of dollars. So what we were measuring, his number is really not relevant to what we were measuring. So as an outlier, you have the option to exclude it from your set of data and recalculate without the outlier in it. And that's really what they should have done there. They should have recalculated that without his salary in there, because his salary really does not represent what they were trying to describe.
Can you request, like, instead of having average, you want the median?
Some places have that information available. Some places they have an outside group calculate that stuff, and they're just publishing the numbers they've been given, and they really don't understand what they're publishing. Statistics can really be used. Uh, I've been hired I worked for a short period of time for the Statistical Research Center in Madison, and they were hired by companies where they had a request for studies to be done, and they were required in some cases by government agencies to do these studies before they could sell a product or before they could make structural changes. So they would send us these requests for a study to be done, but then they would send us what they needed the results of that to be. We really need this to come out like this, So you design it so that it's going to come out that way. See, I mean, when you're doing surveys, gathering information from people, by the way you word the question, does it? Like if I worded a question, are you willing to pay more in your already too expensive taxes to support school lunches? Well, you saw more taxes and you probably stopped reading there. Your answer is no, I don't want to pay more taxes. But if you worded it as, if it means that our children can get better nutrition in their schools, are you willing to pay a little bit more in taxes? Well, now, am I in favor of our children eating better in school? Yes. So, I mean, the way you word a question can manipulate the answers and the results of a survey. So there's a lot of things you can do to manipulate the statistics. Well, like I mentioned on Monday, Mark Twain once said, there are lies, there are damn lies, and then there are statistics. And that's why for me, I mean, I've seen a lot of those things like this salary, statistic. I've seen statistics used in a lot of ways to be deceiving, to try to sell a product or try to convince somebody. I mean, we just went through a presidential campaign, and there's a number of statistics out there that were just absolutely abhorrent. They look at job statistics. Well, are the job statistics including people that have stopped looking for work? Are they including people that have been employed by, government programs? Or, what do those job statistics include? And I think it's, most of your unemployment rates that you see, if somebody's been out of work for more than 9 months, they're no longer considered unemployed. They're considered out of the job market. So they don't appear on unemployment statistics. So if you've had a big loss of jobs and 9 months later, you will see a drop in the unemployment rate, because if they've been out of work for 9 months, they're not considered unemployed anymore. Which to me, it's deceiving. And so you see those statistics, those surveys done. I've seen political surveys done because I've worked with them. Most of the people that are doing those surveys, the people that call your home and say, hey, would you do a survey? They have no idea what they're talking about, what the survey's about. There's a computer monitor in front of them that is giving them a script. Hello, sir or ma'am. Thank you for your time today. I would like to ask you a few brief questions about whatever the topic is. Do you have a couple minutes to answer a couple questions? And they answer yes or no. And there's actually on the computer screen, they click what their answer is, yes or no. And if they click no, okay, it pops up the script. Okay, thank you for your time. Please have a nice day or whatever. It comes up yes. Okay, well, this is going to require you to have a paper and pencil or whatever, let me know when you're ready. And then they'll ask the questions. They ask a question, they click whatever the answer is or type in a brief answer. What they do is they call stack surveys. Let's say you're president and you want to get an approval rating, or you want to publish a survey about what people think of one of your policies that you're trying to propose. What you want to do is you want to be able to put it on the news that a majority of the country is in favor of something you're proposing. So you'd ask a 5-question survey that has nothing to do with what you're asking about, but it's trying to get the person's political views, their background views. And if it comes out that I'm a very conservative person and what you're proposing is something liberal, at the end of the 5 questions, it pops up on the screen for the telemarketer. Thank you for your time. That concludes our survey. Have a nice day. If you get to the end of those 5 questions and that survey indicates that I might be in favor of what you're looking at, then it'll pop up, well, thank you for your time. We just have a few more questions, and then they'll ask those questions. Well, they published a survey. 80% of people surveyed are in favor of this proposal. Well, that's because the ones that they weeded out, the ones that might not be in favor of it, and they didn't survey them. Does that make sense? Oh, it's dirty. It's downright dirty. But, yeah.
I have a question about the unemployment thing.
Sure.
If you like people after 9 months, they're technically not unemployed, and then they go to welfare. Like, are those like?
Technically, unemployment is supposed to last 6 months, and then after 3 months off of unemployment, you're eligible for other programs.
Mm-hmm.
But as far as the statistics are concerned, you're not counted as unemployed.
So like unemployment will go down, but like welfare and those other
Might go up.
go up.
The biggest thing, more accurate than unemployment, is usually I can't remember exactly the name of it now. It's the employment rate, the rate of people that are available for employment who are employed. The job participation rate, that's what I'm looking for. So it's people from 18 to 67, whatever retirement age is, that are capable of working, that are not considered disabled, that actually have jobs. And that is typically in this country right around 55 to 60%. So unemployment rate may be 7 or 8%, but there is about 40% of the people in that working age range that are not working.
So is it like full-time working or part-time working or just working at all?
Well, again, depending on which unemployment statistic or whatever you're looking at, it's calculated differently. For some include part-time as a fraction of unemployment, or some include them as they have a job, period.
So when they tell you, like, how Wisconsin is one on, like, the job market, like, they want people to realize, hey, we're growing jobs in our state or whatever. They probably manipulate those numbers by the questions.
Oh yeah, in the last gubernatorial election, you saw one ad is saying under Scott Walker, jobs has dropped 8%. The next ad, 2 minutes later, under Scott Walker, we have had 7.8% job growth. Well, where are they getting it? Well, they're looking at different sectors. Some of those statistics don't consider minimum wage jobs to be a job, or commission jobs are not considered to be a job because you don't have a guaranteed. There's certain things that are excluded in each of those surveys. I mean, I could look at the jobs and I could make the numbers. I could define what I'm doing in such a way that the numbers are going to show that went down, or I could define it differently and show that the numbers went up. So by defining what I'm going to include and what I'm not going to include. If I include part-time workers, then the job participation rate went up. If I don't include part-time workers, this was actually a huge deal that hasn't really been resolved. When the Affordable Care Act was passed, what was that, 2010? There were a lot of people who were cut from full-time to part-time because you couldn't work more than 30 hours a week, or your employer had to give you health insurance. Well, the big argument is, are those people now employed? And there are like three categories. There's employed, there's unemployed, and then there's underemployed. And by most definitions, they're considered underemployed, but they changed the way they calculated unemployment to consider those people fully employed if they were 28 or more hours a week. So, yeah, there's a lot of things, by the way you define your things, it changes what those numbers are telling you. Let's take a brief look now at center of data. So for the center of a set of data, so again, that's that bell curve, or not center, spread, I was going to say. For the spread of a set of data, that's how wide that bell curve is. I would say the brown curve here is more spread out than the blue curve. The blue curve has less spread. One of the measures of spread we have is something called the range. The range is really simple. It is just the largest number, which is called the max, minus the smallest number, which is called the min. So back to my original set over here in blue, that would just be the 32 is the largest number minus the 8 is the smallest number. So that has a range of 24. That's a pretty quick number to calculate, but it's not terribly reliable. precision is the term we're looking for. Precision is the ability to discriminate to tell the difference between one set and another. I'm going to put two sets of numbers over here. The first set I'm going to put is going to look like this. We're going to do 8, 9, 16, 23, and 24. The other set's going to be 8, 15, 16, 17, and 24. Which one of those would you say is more spread out? Well, if I did a number line going 8, 16, 24. Yeah, this one here, I've got 8, 9, 16, 23, 24. That one looks pretty spread out. The bottom one, if I put it in purple, well, that's 8, 15, 16, 17, and 24. That one's not very spread out at all, is it? So I'd say the top one is more spread out. But if I find the range, what's the range of that top set? Yeah, 24 minus 8 is 16. What's the range of the bottom set? Yeah, 24 minus 8 is 16. They have the same range. So the range is not adequate to distinguish between those two sets of data. So we use something called the standard deviation. Now the standard deviation is a 6-step process, and each step has a name. So let's go through it. Our first step is to find the mean. So I'm going to add those numbers together. 8 plus 9 plus 16 plus 23 plus 24. And divide by what? 5. Yeah, there's 5 of them there, so I'm going to divide by 5. N equals 5. I believe that adds up to 80, so that averages out to 16, or mean is 16. Is that correct? I was wrong last time. 17, 33, 56, 80, yeah. That's 16. So that's just the mean. Step 2 is to subtract the mean from each number. So I've got each number here. I'm doing the top set. 8, 9, 16, 23, and 24. And I'm subtracting that mean as 16. So 8 minus 16 is negative 8. 9 minus 16 is negative 7. 16 minus 16 is 0. 23 minus 16 is 7. And 24 minus 16 is 8. This set of numbers here has a name. It is called the deviations. So if you are asked to calculate the deviations, that's what you are asked to do. You just find the mean and subtract the mean from each number. There will be a separate deviation for each number in the list. Step 3 is to square each deviation. So negative 8 squared is 64. Remember, a negative squared is always positive. Negative 7 squared, 49. 0 squared is 0. 7 squared, 49, and 8 squared, 64. Notice the negative numbers, I did put those in parentheses to square them. When you put them in your calculator, same way, you'd have to put them in parentheses to square them. Or remember that anytime you square a number, you get a positive answer. These here, that list, is what's called the squared deviations. Step 4. Is to find the sum or the total. So I add up this list up here. And I get, what, 226? Does that look right? No, this list here. The squared deviations. If I add those up, I believe that's 226. That is called the sum of the squared deviations. Step 5. Is to divide by n minus 1. What is n in this list? 5. So, n minus 1 is 5 minus 1, or 4. So we're going to take that number, 226, and divide by 4. So what's that, 45.25? No. 56.5. You got her. Divided by n minus 1. Yes. That number that I got right there, the 56.6, not 6.5. 56.5. That is called the variance. Step 6 is take the square root. So take the square root of the variance, square root of 56.5. What's that? That's 7.52?
Yeah.
Okay. That number right there is the standard deviation. Bless you. Bless you. So that's a standard deviation of 7.52 for that top set. Let's redo this calculation for the bottom set. We'll fly through it here. What is step 1? Find the mean. So we add those all up. We divide by 5. We get a mean of 16 again. What's step 2? Perfect. We're going to subtract the mean from each number. We're going to get the deviations. So I've got 8, 15, 16, 17, 24. And I am subtracting 16. So 8 minus 16 is negative 8. 15 minus 16 is a negative 1. 16 minus 16 is 0. 17 minus 16 is 1. And 24 minus 16 is 8. Those are my deviations. Step 3. Square the deviations. So negative, and I'm not going to write it out too much here. Negative 8 squared is 64. Negative 1 squared is 1. 0 squared, 0. 1 squared is 1, and 8 squared is 64. Do you need me to pause for just a second to let you catch up? There we go. Okay. Step 4. Yep, sum them up. So that is what, 130? That's your sum of square deviations. Step 5. Divide by n minus 1. So that means over here we're going to divide by 4, right? Because there's 5 numbers. So what is that, 32.5? that would be your variance. So our last step, square root of 32.5, which is 5.70. That's your standard deviation.
So you're pretty much just thinking, after each step, you're taking that number.
And starting the next step.
Doing the next step.
Yep. So this top list here had 7.52 standard deviation. The bottom is 5.7. So that's telling us this bottom list is much less spread out than the top list. Okay, we're kind of out of time here. There isn't a new homework today, but this kind of discusses some of the stuff that was on the homework from Monday. So you might need this to finish off some of the stuff from Monday. There is a new quiz due tomorrow. I won't be here tomorrow. So like I said, so there's no class tomorrow. Monday, we are going to talk more about statistics. And then next week, Wednesday, will be our test.
I have a question. So
Yes.
what is like the